Welcome to the 10th thematic session of the ASME Journal Mechanical Design webinar. So today we gather here to explore the fascinating world of topology optimization. So we are thrilled to have distinguished speakers from the renowned universities. So by the way, I'm Shikui Chen, a member of the organization team. And I would also introduce two of my other colleagues, Professor Haim Waisman from Columbia University. Hi, can you say hi to the audience?
Hello, everyone, and thank you for attending. This is a wonderful session.
And also Professor Faez Ahmed from MIT. All right.
Hi, everyone.
And this will not happen without the support of the ASME journal. So Caroline, could you speak something?
Sure, yes, thank you, Shikui. And I'd like to thank Shikui and Faez and Haim for organizing this amazing session. I'm really looking forward to hearing these talks and discussing them a little bit more. So here at the Journal of Mechanical Design, if you haven't met me, I'm Carolyn C. Prasad. I'm the editor-in-chief. And we're always happy to welcome suggestions for amazing webinars like this one. So we typically host them quarterly. And we're really look forward to the opportunity to highlight different streams or threads of research that are being published in the journal. And this topology optimization webinar is a great example of that. So if you have ideas for webinars or special issues that you'd like to help lead, please reach out and let us know. But thanks especially here to Shikui, Faez, and Haim for organizing this great webinar. And I'll turn it back over to Shikui to get started.
Thank you, Caroline, and also thank you, Amy. So without further ado, let's introduce the first speaker, Satya Peddada from UIUC. So the title of the paper and the presentation is Towards Holistic Design of Spatial Packaging of Interconnected Systems with Physical Interactions. So Satya, please.
Yeah. Thank you, Shikui. I'm really thankful to you for introducing me. And just a quick introduction of myself. I hope everybody can hear me clearly and see my screen. Yeah, I'm very glad to present today at this webinar. I'm Satya, basically currently an adjunct research assistant professor at the University of Illinois, Urbana-Champaign. And I'm also working for the Ford Motor Company as a research engineer in the electric vehicles design research team. So I'm currently having two positions here. And I'm very glad when I heard that I've been asked to present on this very nice topic called as SPI2. I'll be discussing more on this and the relevance of this topic with topology optimization, which is a theme for this specific webinar. And this research is basically based on my PhD research back in Illinois, and my thesis advisor was Professor James Allison. Most of the design research community here might be definitely knowing him, and he works mostly on design optimization problems of various engineering systems. So without much further delay, I'll just go into the topic. So I'll be introducing from this paper. This paper is basically a review paper. We can also call it as a position paper on how it emphasizes the importance of SPI2 design research. Basically, it introduces what is SPI2 design research and the importance of SPI2 design research in future and what are the current bottlenecks we have. It's a very grand engineering design problem. So I think you'll definitely appreciate at the end of the webinar how important it is to focus on this problem from different angles. Like industries, researchers really can have a lot of scope in this research problem. So I'll describe what the problem is and then what are the current bottlenecks that industry and researchers are facing in this SPI2 theme, and what is the current status and what is the future vision that we are seeing for this problem, and why there's a strong need for having new design representation breakthroughs in order to solve such design problems, and how do we formulate the topology optimization problem for a SPI2 system. And one viable framework has been presented in this paper. And that viable framework is this two-stage SPI2 design automation framework. I'll be giving a brief overview because of time limitations, but if somebody has any questions, feel free to reach out to me at my email address, which will be shared at the end of the slides. And at the end, I'll present the conclusion and future research items in this topic. So what is the holistic SPI2 design research problem? So if you see here on the right of your screen, there is this fighter craft. And under the skin of fighter aircraft, you see hundreds and thousands of components that are cramped in tight space, and they're all connected with pipes and ducts and wirings of various sizes. And basically, a SPI2 design problem is where you need to optimize the amount of space occupied by a given system, subject to constraints like how do we place and orient those complex components in tightly constrained spaces, finding collision-free routings for interconnects of various types, such that they meet the size, space, and shape requirements. And all these components like interconnects and different 3D objects for a given system are immersed in spatial fields, like physical spatial fields, like thermal. There's a lot of heat loss and thermal radiation happening. There's hydraulic pressure due to movement of fluids in such systems. There's electromagnetic radiation. And it's not just packaging of these systems in tight spaces. You should also make sure that it goes beyond geometry. The optimization problem is not just geometry optimization, it's beyond geometry optimization. For example, how do we ensure that, for example, in a given electric vehicle, the battery must be placed in an optimal location so that its range is high. So at the same time, it is at an optimal temperature. So the performance should be also based on some physics considerations. And at the same time, even though we package very tightly a given system in space, in the future, it should not be difficult to do some overhaul, repair, or maintenance. So how do we package these components in such a way that those components which are highly reliable are in the core of the system, and those components which need to be replaced or which are critical and unreliable might be on the outer side of the system. So there are lots of design considerations in this spatial packaging problem. So the holistic view is basically how do we ensure that component placement, interconnect routing, physics considerations are taken together simultaneously. In earlier research, basically this component placement and interconnect routing are handled separately in a sequential way, due to which there is a lot of synergy that is missing, and we get some suboptimal results. But is it possible to simultaneously conceive of a design problem where we can address all these issues together is what SPI2 research is looking at. And just as you see the way the problem is set up, it spans multiple industries like aircrafts or electric vehicles, or even biomedical systems like a pacemaker or any other device. It's a 3D system which contains components and interconnects. So any 3D system, any industry that contains this kind of configurations comes under the SPI2 design class of systems. So that's what is very interesting. So how do we do the optimization that is actually best for the overall system is the main consideration here. So just getting into why is it a costly bottleneck across many industries? So current practice, if you see lots of industries, they have advanced knowledge and tools for simulation, design optimization. But the thing is, for complex systems design at larger scales, we basically break up the problem into different parts. So is it possible to have in 5 to 10 years down the road, simulation software or something where it can spatially package and find various configurations for a given system for different system performance metrics? Is it possible to do that? So that's something that SPI2 can offer. The issue that happens with most of the industries is when it comes to actual design of complex systems, they depend a lot on manual decisions. For example, how do you make sure that you fit, for example, you take an aircraft, how do you assemble the aircraft? Lots of conventional methods are used where there's a lot of difficult things happen when you need to maintain or repair such systems, and you need to just throw away those systems if something is not proper. So how do you make sure that even repair and maintenance can be done properly and spatially packaged in such a way that all these different life cycle considerations are also met? And at the same time, to conceive of different configurations of a given system manually is very difficult. The human cognitive space can only conceive of a few components and interconnects together, but when it goes to larger scale systems or complex systems with physics considerations, manual SPI2 design is really a bottleneck. And that's what we are basically facing nowadays. And for the current requirement of technology improvement, we need to have better softwares and better tools that can perform this SPI2 design research. And for example, why has the SPI2 design not progressed? Because Most of the design automation problems which we solve are very simplified problems that have simple representations of the system, and also we don't generally consider multiple performance metrics together. Therefore, this is a very grand design engineering challenge. So, for example, considering both packing and routing together of components and interconnects is a very challenging problem, because packing, which is 3D bin packing, and 3D routing are NP-hard problems. So those are familiar with mathematics, combinatorial problems. It's very difficult problems. So how do you make sure that we find those design representations where packing and routing can be done simultaneously? So both discrete and continuous ways of solving this problem is required in this case. And one good reason for optimism is the last few years at Illinois and other partners with Illinois, we have found out a method where we can represent a given SPI2 system, like the components and its interconnects in space, as a spatial graph. And the advantage of that is you can represent your components as nodes and your interconnects as edges of that graph. And that graph can be projected on a 2D plane with crossings as shown here. And the advantage, another advantage of this representation is it can be also written as a unique polynomial, and hence you can enumerate various configurations of a given system by enumerating the graphs, and you can check if the graphs are isomorphic or not by comparing their Yamada polynomials, which is a mathematical polynomial that comes from knot theory. So this is one interesting way we have made progress in this design, SPI2 design automation. And just going back several decades ago, previous SPI2 design automation involved where packing problem was only looked at separately by Professor Faez and Professor Qian. They're really well known in the design research community. In 1996 to 2008, packing and routing was seen a lot by Professor John Qian. And from 1960s, we have been solving many routing problems, both in robotics, and lots of computational geometry researchers are solving this problem. But it's been solved separately in different cases like 3D path planning or chemical process plant layout routing. And then interference, for example, or non-overlapping of different components, 3D geometry interference problems have been solved since lots of decades. And what's now interesting is from 2010 present, we are seeing multi-physics topology optimization problems and geometry projection methods coming up. And Professor Norato, who is also well famous in this design research area, is looking at these geometry projection methods. One interesting point with geometry projection methods is you can represent the conventional topology optimization methods yield like organic structures, which are very difficult to manufacture. But when we use geometry projection methods, those methods use stock materials like bars or solid objects as the primitives. And when you do the topology optimization, the object shapes remains the same. So that's the advantage with geometry projection methods for SPI2 design. And that's the connection where in a SPI2 design problem, you have components and interconnects. When you optimize them in space, when they move in space, when you optimize the overall area or the volume with respect to physics, geometry projection methods work well, which is a topology optimization method that preserves the shape of the objects and the shape of the tubes or the interconnects. So that's where we got inspiration to use that method for SPI2 design research. I'll describe in a little more detail later on why it's important. And each of these different independent problems like packing, routing, physics considerations, and topology optimization will be clubbed in the SPI2 design automation research, is what has happened in the past few years at Illinois. And we are trying to solve this problem more comprehensively at larger scales for industry relevant systems. And so in summary, what's there is current SPI2 design practice in industry. It depends a lot on CAD, CA support. Most of them are based on human decisions, direct human decisions, and design automation is, I would not say it's not completely used, it's used, but it's pretty slow when it comes to making larger scale decisions or finding out new configurations quickly. Most of them are incremental. But what we are looking into future is if we have design tools for SPI2 that can support exploration of new configurations quickly and adoption of these tools into the industry, then it can accelerate the generation of new technologies and adoption of new technologies into the system. So there's a big chasm that needs to be covered quickly. And one design representation breakthrough that we have got at Illinois is basically what makes SPI2 design really hard is you have continuous design decisions, which are basically which include like how do you place the components or in different positions while you optimize the overall packaging area, and at what is the shape of the components and how do you orient the components. So these are all continuous design decisions. At the same time, there are spatial topological changes. For example, if there are two interconnects, like should that interconnect go under this or over this, or if there are some hollow objects, should it go through this or outside this, are discrete decisions. So how do you make sure that you take care of all these decisions? So you need a design representation that can support that. So in knot theory, we have found something called as spatial graphs, which can distinguish between two different spatial configurations. For example, on your left, you can see a spatial configuration S1 and S2 on the right. Both have the same connectivity, which means the components are connected to the same interconnects, but both are having different spatial topologies. For example, interconnect 1 and 2 here are entangled, and unless you cut it, you can't get the new configuration like in S2. So these are the topological decisions I'm talking about that need to be taken care while optimizing such systems. And again, if you see another layout here where an interconnect is going from A through C, A to C through B, and there's another interconnect going outside this hollow object B. So these are again topological decisions that are discrete. So how do you make sure that while you optimize the locations of the components, you also find out new configurations with different topologies? So with the help of a mathematics professor at UIUC, Professor Nathan Dunfield, we came up with this design representation where we can represent a given SPI2 system with a spatial graph and enumerate all the graphs for the given system, and then optimize each of that graph with respect to its spatial, physical, and other design considerations. So before we go into the two-stage framework, which is one viable framework. In the future, there might be other viable frameworks by which we can do SPI2 design automation. This is just one example which we took in the paper that we explored a lot. The main design optimization problem here is objectives include system utility, for example, overall volumetric density or physics performance of a certain system or other all considerations. And the constraints for a SPI2 problem are geometric and topological, functional, failure modes need to be satisfied, assembly disassembly constraints, like how do you assemble the object when you're packaging it, and accessibility constraints, like is the component accessible for repair, and how do you make sure that that constraint is met, and even manufacturability. Once you design a system, how easy is it to manufacture it and make it into production? And the design decisions are, like I said, topological decision, which is a discrete decision. Continuous decisions include like locations, sizing of the components, shapes, pipe sizes, and all, orientation, control of the flow of fluids, and other tuning parameters. So this problem basically currently shows how lots of engineering disciplines need to be integrated in order to solve this very challenging problem together. So this is just an example of how many disciplines we're currently integrating, with lots of researchers focusing on this problem as research is going in this direction. Coming to the one viable method to solve this SPI2 design problem is, like, let's say we have a given system where a user gives the component shapes, geometries, and the connectivity of the system. What we can do is we then, in stage one, we take each, like the initial configuration, and we use spatial graphs to enumerate different discrete configurations. And in stage two, what we do is we take each configuration, we apply geometric projection topology optimization method in order to optimize its overall volume with respect to physics considerations. So I'll be quickly going through what is the stage one and stage two. The reason we separate this optimization problem into two stages is stage one is taking care of the discrete part where we enumerate as far as possible different unique configurations or topologies. And then each configuration which is unique in stage one is taken into stage two for continuous multi-physics layout optimization. And there's a journal in JMD that we published where I'm the lead author, and you can look into that in more detail about this two-stage design automation framework. And stage one, like I said, if you take a given configuration, what we do is we enumerate that. One simple example is in this configuration, you have different classes, and each class is a unique configuration. For example, class one, all these layouts are of the same configuration, because if you see this one, it has 0 crossings, this one has 1 crossing. If you just twist this in space, you get this configuration. So it's the same topology, but class 1 and class 2 are different topologies. Unless you cut the wire, you can't get this configuration. So what we did is we used some mathematical techniques in order to enumerate such spatial topologies which are discrete for each configuration. And then we applied it on a Ford fuel cell packaging problem. Here you see a fuel cell. We enumerated different spatial graphs of it, which are unique, and we got different 3D configurations of each one. And then we optimized those configurations for space, and we got 3D printed designs like this. So this is one simple example of how we applied SPI2 design automation, where we automated the configuration enumeration and then optimized it with topology optimization and then 3D printed it. It's just a quick sequence I'm showing here. And stage 2 is where once we get the unique configurations, how do we apply topology optimization using geometry projection? Like I said earlier, topology optimizations, which are conventional, give organic structures. But what we want to do is we want to preserve the component geometry in SPI2 continuous optimization. And geometry projection is a method where primitive objects, which are solids, are projected onto a mesh. And then what we do is basically, for a SPI2 system, we have components and bars which represent the system. And then here is a simple optimization formulation where we want to optimize the bonding box volume of a system, where the intersections between different components and interconnects are made sure that they don't intersect. So you have some device constraints, interconnect segment device constraints, and all other combinations. And at the same time, physics constraints, like making sure that no temperature of the device is going beyond limit, or the head loss constraints are maintained when fluid is passing, fluid temperature, and all those things. So here is a very simple example. I have more complex examples of real world systems, like I showed the Ford automotive system example. But here is a simple system where we take a 3-component system with interconnects, and then we optimize it with topology optimization method using geometry projection in order to get different layouts for different constraints. For example, if the head loss constraint is 2.5 meters, it makes sure that it is met. And if there's no head loss constraint, you see more farther components which are much farther from each other. Similarly, if you have an 8-component system, when you optimize it for head loss, you see.
Oh, excuse me, Satya. So
yeah.
Please be kindly reminded. So each speaker at most has 20 minutes.
Sure.
Thank you. Yeah.
And so how far I have? Yeah, I'll try to quickly finish. And so this is a simple example of how the optimizer takes a smart decision depending on the constraints, what kind of result it gives. So you can just imagine with components of different geometries and shapes and different interconnects, how we get different spatial package solutions. So that's something I wanted to show here quickly with this example. Lots of details are there in the paper and other related papers with respect to SPI2 design research, so you can look at them. And in conclusion, I would say that holistic SPI2 design automation is a vast research area that's currently expanding, cutting across multiple disciplines. And here's one method which we presented that optimizes the component locations and the interconnect routing paths based on physics performance. But lots of other methods can be possible and which can be applied for industry-relevant applications. And future research questions include this, like what design optimization frameworks can be newly framed, and how does the problem difficulty scale with respect to number of components or interconnects, and what kind of new parameterizations or representations are required, etc. So as a quick snapshot of some SPI2 research activities at Illinois and its other partners include applications to various systems, microelectronics, HVAC system design for buildings. So it spans all over, even biomedical device design, etc. So these are some of the researchers who I'm really glad that supported me during my postdoc and PhD at Illinois, and currently as an adjunct professor at Illinois. So I'm thankful to all of them, and thanks everyone for your attention, and thankful for this presentation.
Well, thank you, Satya. Topology optimization for additive manufacturing using neural networks. So Burak, so when you feel comfortable, you can start. Thank you.
Okay. Well, thank you very much for inviting us to this great meeting. I'm joined here today with our co-authors, Hongri Ray Chen and Aditya Joglekar. And this work is conducted at CMU, and our collaborator is Professor Kate Whitefoot. Today, we will be talking to you about concurrent build direction, part segmentation, and topology optimization that's geared toward additive manufacturing, and we're using neural networks as geometry representation. All right, so so that we can explain, let me just try to minimize this window. All right, there you go. So that we can explain the input-output before we get into the details, we're prescribing a problem in which we are providing as input the material properties that we're interested in using, the boundary conditions, displacement and load boundary conditions, and the number of segments we want the final part to have. This is in contrast to monolithic structures that are pretty pervasive in additive. But with these inputs, we are hoping to produce an output in which we have a single topology and we have a segmentation of that topology into however many segments the user has provided as input. And for each of the segments, there's going to be a print orientation that is also an output. So in this work, the topology, the segments, and the print orientation for each segments are concurrently optimized rather than sequentially. So how is this achieved? So we have 3 neural networks that are working in unison to produce material distribution hypothesis that is then minimized across an objective function that we will talk about. Uniquely, so we're using neural networks as a geometry representation. This allows us to decouple the complexity, the degrees of freedom in the design domain from the difficulties in the simulation side of things, for instance, the finite element analysis that's needed. So we have this decoupling that's allowed through the neural network, and we're building off of the ideas that have been presented in the last 3 to 4 years. All right, so our neural network-based approach is based on Krishna and Suresh's group in real-time topology optimization using neural networks. These neural network approaches are not a data-driven approach. Rather, these are online methods that basically take the given problem and then they try to optimize a structure using the neural network as the optimization engine. There have been many works that try to design structures that are suitable for additive, primarily in overhang angle control, for instance, that minimizes the amount of overhang. We're also inspired by these works that try to minimize these quantities. Our past work in part segmentation for additive manufacturing is not redesigning the structures, but it is trying to find the proper segmentation, decomposition of an initial structure into its subgroups, and then we're trying to optimize their print orientation to create compact build volumes. So these are all pieces of work that inform the work that we're about to present. Also, topology again and its variants have been looking at using generative adversarial networks in order to produce topologies, and these are trained with prior previously established solutions. This work is in contrast to these data-driven approaches. Like I said, we're not using a data-driven approach, but rather an online approach. Finally, there's existing commercial software that look at some of the criteria that we're also interested in, like the total amount of support structure. However, these tend to be working for fixed orientations in the build chamber, and they're trying to optimize the support structure accordingly. The one thing I'll say is, even though our inductive bias is support structure minimization, overhang minimization, in real practical applications, it is not always the case that one would want to minimize the support structures, because many times support structures can also be used as a conduit for heat conduction and so forth. But ours is kind of us taking a simplified approach to support structure minimization. All right. So our work is primarily on this left-hand side, and we're kind of joining these works that were presented in the past by us and others. All right, so our main contributions, we believe, are an analytical solution to the density gradients that we obtain from the input-output relationship using the 3 neural networks. This allows us to create a fully differentiable pipeline where we have a combined build direction, part segmentation, and topology optimization that is enabled. And the different pieces of this architecture are modular. You can turn on and off different pieces, for instance, to totally eliminate segmentation or prevent build direction optimization if needed. Our architecture looks like this. Like I mentioned, it pulls together three different networks. The first network is a topology network that takes X, Y, Z spatial coordinates that we can sample in the Euclidean space, and then it will provide a density for each of the X, Y, Z. So you can think about this as a material hypothesis generator. The segmentation network looks very similar to the topology network. It takes as input XYZ domain coordinates. It passes through a similar set of functions, including Fourier layers, except it doesn't produce a density at the output, but it creates a classification, basically a segmentation using the softmax layer as the segments. As I mentioned earlier, the number of segments is an input by the user, so that it is not a number that is automatically determined by the system. The final piece of the network is a print angle optimizer for each of the segments that are computed in the segmentation network. We're also going into optimizing the orientation. All these three work together to produce the compliance information that is computed through FEA, as well as the overhang and a volumetric proxy to the support structure. And these are all joined into a loss function that is minimized. So this loss signal is then passed into the earlier networks through backpropagation to create the funnel structures. This is one example. And like I said, the segmentation is implicit in this, where we have access to the different segments and their print directions. Okay, so the two networks, the topology network and segmentation network, are inspired by these two great pieces of work that have been published rather recently. And we're joining them together and then combining a print angle network to them to achieve this concurrent optimization. But if we were to go under the hood in these networks, the topology network is using a Fourier layer to represent the geometry. Basically, for any XYZ point, we have multiple different filters, basically cosine and sine functions at different frequencies that allow us to then join their outputs through weights, linear layers, into a dense MLP. And then from there, we go into a sigmoid function to determine solid or void. The segmentation network is using a very similar principle, similar geometry representation, but like I said, the last layer is a softmax layer that allows us to do some segmentation on any given XYZ. The final layer, the final network, is the print direction optimization, where the input to that network is actually a bias, simple bias term of 1, and then we're optimizing the weights associated with the Euler angles in order to minimize the joint loss function. So the mathematical details are provided here. They are very similar in the two networks, and the last print angle is actually quite simple. All right. We think an important observation and contribution we had was to show that the analytical gradients that we can compute throughout the topology network as well as the segmentation network, we got similar results if we were to use automatic differentiation. So basically, the results that you're seeing here with the red and blue arrows are the differences in automatic differentiation versus using the analytical gradients in the gradient calculations. These two different halves are both aimed at finding the density gradient so that we can drive topology optimization. But this is just almost like an internal validation approach to show that the analytical gradients are actually valid in this case. However, in practice, we saw that it doesn't make a huge difference whether we use the analytical gradients or the automatic differentiation for density calculations, gradient calculations. Performance-wise, they're actually pretty negligible. The differences between them is pretty negligible. All right, so at the heart of our computations for compliance, we used a SIMP-like approach where we are using finite element analysis that is then applied on a mesh grid that is independent of the original XYZ points that the networks are taking as input. In fact, this decoupling of the geometry representation from the analysis domain is one of the unique features of this neural network approach. and we're leveraging this previously presented idea. For passive elements where domain materials should not appear, we can enforce that with a simple L1 loss in the neural network, as well as creating symmetrical results. We also attach another formula that gets incorporated into the network. So symmetry constraints as well as passive element enforcement is rather straightforward with these neural network representations. Here we're seeing the convergence for a simple based approach in the compliance versus the neural network. We see that the neural network is slightly faster in getting under a particular compliance value, but this is not always consistent. It is not always the case that the neural network is kind of faster than the SIMP. In fact, if we wait long enough, we do observe that the SIMP gets slightly better compliance over our approach of using a neural network. But overall, this was good in seeing that both the volume fraction constraint as well as the compliance as the objective function, both approaches, SIMP and neural network, are achieving similar results. The oscillations that you see here, it is due to the fact that we're using stochastic gradient descent in our back propagation algorithms. This slide is here to show how we formulate a height penalized overhang formula. This is basically a proxy for support structure volume. Previous works, well, most significantly, the work by Wang and Chen, have looked at minimizing the amount of overhang. What we're doing is we're slightly extending that by not only computing the area of the overhang, but also the volume underneath. And all of that is tied to the build orientation that we will ultimately optimize. So the angle for printing is taken here as a parameter that allows us to formulate the overall volume, support structure volume, and create a differentiable function that we can use for backpropagation. So this is a slight improvement extension over what has already been published. Finally, the loss function, as I mentioned, is looking at compliance. It tries to minimize the overall compliance. We have a target volume fraction as a constraint, and we're trying to meet that as closely as possible. And finally, we're trying to minimize the overall height penalized overhang area. So these three terms constitute the loss function, and the gradients of the density can be computed relative to this loss function using the information we just shared previously. So what happens if we use this height penalization versus if you don't? So without height penalization, the height penalization essentially means the following. If our system is going to create overhangs, how far should those overhangs be from the build plate is the question that this is answering. Because this is going to impact the amount of support structure that needs to be built underneath. With our system, it is able to penalize tall areas in which overhang is likely to appear. So for instance, our system is creating a gap here, but if you don't account for that height, sometimes you create these bridges which will require quite a bit of support structure, which will be a major cost driver. So that slight extension allows us to capture these nuances in support structure generation. Here are some results of using part segmentation relative to not using part segmentation. We're achieving slightly better compliance when we input 3 segments as the desired number of segments as opposed to a monolithic build. And for each segment, we automatically minimize the support structure by laying, for instance, for some of the side walls horizontally to minimize support structure. Obviously, there's no free lunch. I mean, the fact that we're creating these segments and optimizing each concurrently does not mean that this overall design is better than a monolithic version. At a minimum, we have to now pay some price for assembly and generating those assembly surfaces for sure. So there's a trade-off, but we think this multi-segment optimization may be an interesting contribution to the community. Finally, here are some results showing the conventional approach for height minimization as well as compliance minimization versus a concurrent approach where things are done jointly. The lower the C, the better. The lower the H, the better. in these two halves, you see that our approach is trading off compliance. So it is achieving worse compliance in hopes to minimize support structure. So you can definitely see a trade-off happening here, because unlike the case where we are doing concurrent optimization, the compliance values can be further minimized. So ours is creating a trade-off between those two forces, if you will. Some of the limitations. So as I mentioned, the segmented parts require assembly for sure. So there's going to be additional work that's needed to design the mating surfaces that go into a multi-segment segmentation. So we are currently working on this aspect to automate, to fully automate the assembly instructions also. It is a hard problem, but it is something that is actually quite exciting. The other two things that I just want to mention that we think is tied to what we just presented, in a recent work that is just recently accepted to Journal of Mechanical Design, we are showing how a neural network-based topology optimization, its convergence can be significantly accelerated by providing input fields that have to do with the initial unoptimized design domain. Uniquely, if we were to provide, for instance, the strain energy as a conditioning field to the neural network no longer takes as input XY or XYZ, but it is also taking the strain energy field as part of its input. We see that the convergence can be accelerated. So this was a discovery that we came across when we were trying to make the convergence faster. The overall results, the final results, the compliance is probably comparable between using the initial field versus not. But if we were to look at a target compliance, we can meet that in a much fewer number of epochs compared to not using that kind of an initial field. I'm going to skip this slide in the interest of time, but we would be happy to share more details. One last piece of work that we are super excited about is actually going to a totally mesh-free topology optimization using pin-like structures. This work is now accepted to engineering with computers, where we are showing how two networks, a density neural network and a displacement neural network, can work together to create a totally meshless topology optimization. So there is no FEA calculations in here. We're not creating an FEA matrix. Everything is done at XYZ, and what we're doing is we're minimizing the strain energy computed at every XYZ. So there are two networks that are working together in order to minimize the overall compliance in this way. So the output is computed in basically a sampled set of points rather than on a mesh grid that uses FEA, for instance. The results that we see are currently promising, even though there's still room for improvement. For instance, this direct mesh-free topology optimization, even though it is slightly worse than the SIMS compliance, for instance, 286 versus 273, the time is actually not far off from an alternative meshless topology optimizer that is taking a lot more. So ours is striking, we think, a balance between fast convergence to a good solution, even though there's still some improvement in the compliance. However, in certain other boundary conditions, like the one that is shown here, ours is able to get below the compliance of the conventional SIM, even though the alternative, the ANTOPO that was published about a year ago, is actually getting the best compliance out of them. So we are still exploring this space of how we can make meshless topology optimization a reality. But I think, including our work and other people's work, I think there is quite a bit of energy in this field nowadays. Thank you.
Okay, thank you very much, Professor Kara, for a nice presentation. Our next speaker is Professor Faez Ahmed from MIT, and he will give us a review on deep generative models in engineering design. So, Ahmed, please.
Thank you. So hopefully everyone can see my screen. Great. So Today, I was invited to talk about deep generative models in engineering design, and specifically this paper with my students, Lyle, who is the first author, and Amin, where we talked about a review of how deep generative models are used in different engineering applications. And there was a special focus on topology optimization. However, when I was preparing this talk, I felt that a lot has happened between the time the paper was published. So I thought I'll talk about a few other things specifically around deep generative models, metrics for deep generative models. Both of them are published in design community. And then also some recent work around using diffusion models and diffusion optimization models, which were published in AAAI and will be published in NeurIPS 2023. Great. So let's kind of start with like, what's our overarching motivation? And the overarching motivation is, how can AI enable humans to create better designs faster? And specifically, we will be talking about generative AI or deep generative models. Now, just to give you a quick introduction of people who are new to this field, generative AI is a field of artificial intelligence that uses algorithms to create new and original content. It could be text, images, videos, or other media. And this definition is provided by ChatGPT, which is a type of generative AI model. Having said that, there are many models that have existed over the past decades and even before that, including variational autoencoders, GAN models, diffusion models, GPT, mixture of Gaussians, and so on. And when you really think about what are these models doing, like at a fundamental level, these models are looking at some data. So in this case, the green distribution is the one-dimensional data. And effectively, they are fitting a function to approximate that data. So imagine it's like a simple mixture of Gaussians or different types of models. Of course, the dimensionality that we work with, so for example, a topology optimization problem with a 1,000 cross 1,000 grid is fitting a function in a 1,000,000 dimensional space, which is much more complex to learn. And why now? Why are we talking about these fields now? So just to give you an idea of like, these are the quality of images generated by different models across years. So from 2014 up to 2019, we had generative adversarial networks, which were quite popular. And since 2020, we are seeing more and more of diffusion models, including DALL-E 3. And you can see how the quality has changed. And in fact, funnily enough, I looked at, so this paper, which I'm presenting, was submitted to JMD in 2021. It was published in 2022, and I'm presenting today in 2023. And if you look at the quality of an image generation by one of the top image generator models in 2021 to 2022 to 2023, for something simple like a group of elephants walking in muddy water, you can see there's a huge improvement within a very short frame of time where we are seeing better sample quality. Or effectively, we are seeing basically models which can capture very complex distributions and create things that are synthetic. So, I mean, as a result, not surprisingly, there has been a lot of interest in engineering design, and we are definitely not the first ones by far to think about this. There is a lot of people who are thinking about different aspects of how deep generative models can help in engineering design. Applications including topology optimization, microstructures, airfoils, 3D shape synthesis, manufacturability, and so on. And a lot of these are discussed in our review paper. And to give you kind of like a recipe of like how to think about these deep generative models, again, from the paper, like a lot of times people start with some design problem. It could be topology optimization, material, airfoils, mobility solutions. Then they move on to thinking about how do they represent this design? Are they using implicit functions? Are they using voxels, images, tabular data, graphs, mesh, point? Once they have done this, they often need to collect large data sets. The models learn from these data sets, and then they pick the models that are suitable. It could be GANs, VAEs, like there is more recently diffusion models, but there is a lot of other models that are also available. And each one has its own advantages and disadvantages. So you take your model, you pick your model, and you apply basically for some form of design synthesis where you want to create new designs. And then there are some things which people care about in the literature. People have been looking at iterative retraining, latent space optimization, and auxiliary loss functions, which can improve the training, say for manufacturability or compliance and so on, in the case of topology optimization. So since this webinar is about topology optimization, I wanted to talk about why should generative AI care about topology optimization, and why should topology optimization care about generative AI? And I'll give you some preliminary examples of things that we have discovered. So first of all, just to give you a quick overview of like when we're talking about structural topology optimization, the standard problem, and this is a 2D problem that we are showing, is that you are given some boundaries, you're applying a load, you want say 40% of the material, you run a standard optimization solver. SIMP is a very popular one. You can use implicit functions. There is a bunch of other methods, and you find the optimal distribution of materials in this space. And this works quite well. There are some parameters like penalization, filtering that you have to fix. But every time you run an optimization, you almost always start from scratch, which means that over time, you are always ignoring all the past optimization runs that you have done. On the other hand, the data-driven approach effectively, often what it does is it collects a huge data set of many different loads and boundary conditions. So this is like one example of optimized topologies. Then it might train a conditional generative model. It could be a VAE GAN diffusion model. And then once the model is trained, the hope is that given any new condition, it can instantly generate new designs that are optimized. Basically, in some sense, it's learning from experience, where it says that I have seen so-and-so boundary conditions being applied, and since it's a data-driven approach, I know that this, given this new conditions, most likely the structure will be so-and-so. And there are many, again, approaches within this we talk about in the paper, like VAEs, GANs, super resolution, iterative training, human guidance, real-time synthesis, where you're generating things in real time while you're changing boundary conditions, physics-based models, and so on. And the benefits, a lot of times, I think the benefit you can, overall, the goal is, can we get better designs faster? Once trained, these models can produce designs very quickly, especially for high-dimensional data. I'll show you some results for that. Also, they can uncover novel and unconventional designs. They can reduce manual input and other things. However, in practice, when we apply these models, if I apply like a standard GAN model, what I would often see is that on the top line, you see, or bottom line, you see the ground truth, and the top line, you see the generated designs by a deep generative model. And you can see there are some issues. It's the good thing is in the last case, it's coming up with something completely new, but a lot of times it's disconnected and not really as clean as what the SIMP model would give in this particular case. And there are many challenges behind running these data-driven approaches. Generalizability is the biggest challenge. Some of the other challenges are we have to define design performance, like including functional performance is quite critical. The data sets that are available these days are generally very small. And as a result, since these data-driven approaches depend on data, there is a lack of performance. Finally, we want to create designs that are very novel and not just trying to exactly mimic the optimal solution. And we want it to be fabricated. They should be physically feasible. Now, one of the challenges on why I showed you some results on why these models struggle. And one of the challenges is that most generative models are developed for multimedia domains like images and text. And their goal is basically some notion of statistical similarity. So they are looking at KL divergence. Basically, they are trying to be as similar to the training data as possible. So in a recent work, we started looking at this problem of statistical similarity, and you can see two topologies which look very similar in the pixel space can have huge difference in the performance space. And it's not just the performance space. There are many other things like constraints, conditioning requirements, and so on. So this is a paper published in CAD where we look at many different metrics that people should care about, and not only in training the models, like effectively telling the models that you have to think beyond statistical similarity, but also evaluating the models on how do we evaluate, for example, the diversity of the design. So in this particular example here, you see there is a SIMP solution. There is a solution by one of the generative models where you see that it's almost trying to mimic three of the designs it generates are very similar to the SIMP solution, but there's another model which generates very unique designs for the same problem. But again, there is a trade-off here that it may not be as compliant as SIMP or the other models. So there are some trade-offs that we should be aware of and thinking about how to evaluate these models. So inspired by these, we started thinking about, we wanted to create a generative model which knows more about performance and is also somewhat aware of the constraints. And we started looking into this idea of diffusion models. The way diffusion model works, and this is like if you're using any text to image model, most likely they are some form of diffusion model. Effectively, it starts with complete noise, incrementally adds noise it starts with the design, incrementally adds noise until it gets complete noise. And you train a neural network to denoise it at every step. Unlike VAEs and GANs, this is an incremental approach where you go step by step and slowly improve the design from complete noise. So we can train these diffusion models. But then the problem is, again, that we have not told it about compliance and any other like performance metrics. So we started introducing this idea of guidance, where you can take, like if I want compliance, I'll train a separate neural network for compliance, floating material. If I like aesthetics, I'll create another one for aesthetics. And all of these models can be used as a guidance for the diffusion model. And the best thing about it is if you train your diffusion model today and 5 years from now, you decide that you want something else, you can just change your regressor and classifier and you don't need to retrain your diffusion model. So just to give you an overview of the architecture, you can look at the AAAI paper here, but we define different ways of conditioning. In fact, one of the conditioning methods is inspired by what Burak was talking about on how using fields. So that's one of the input to the model. You can see here the conditioning fields help a lot. And we introduce these regressors and classifiers. And what we see is that we can generate optimal topologies using these diffusion models. And when we compare it with generative adversarial networks, we find that it's almost 8x less compliance and 11x better in floating materials. So here you can see in the middle, you have SIMP solutions. On the right, you have the solutions from TopoDiff, and you have some conditional GAN models. And in many cases, it generates better designs, but also sometimes it would go and generate things that the SIMP didn't think about. So it also sometimes can be more creative. So this was inspiring, but again, there are issues with it because first of all, this approach is quite slow. It's an incremental approach. So we started thinking about how do we speed it up? And when talking to colleagues, a lot of times people say, why do you even need to do generative models? Like, why not just use topology optimization? Like, why are we trying to think about using generative model? And the answer for us was, well, why not use topology optimization? So we came up with this new approach where we said, instead of training these models on optimized topologies, the final optimal topologies, what we would do is we would use a separate approach where we learn from the path that the optimization took to reach the optimal topology. So in this case, the top line is the path any optimizer takes. So this is for demonstration, we have used SIMP. But SIMP goes from complete material to an optimal topology, and diffusion model goes from complete noise to an optimal topology. And we showed a new way that we can map these two together. And the model at the time of training is learning from entire paths. And if we do that, we found that this can significantly make the topology of the generative model faster and also more accurate. In fact, in the case of 256 cross 256 domain, it's almost 40 times faster than SIMP. Having said that, there is a difference that one is running on GPU and one is running on CPU. So this 40x should be taken with a grain of salt. Great. So that was one approach. And effectively, what we are doing is we are taking optimization and merging it inside the generative model. And there's a lot of like tricks on how we do this. The next thing we started looking at is how do we take topology optimization and use the generative model to augment topology optimization, which means that the generative model basically gives the initial point or the initial solution from which SIMP starts. And effectively, we find that with very few optimization steps, this can enhance both the results of either doing just SIMP or just generative models. And as a result, we have found some very good results. The paper is online. One thing I want to highlight is a lot of it is data-driven, and really the restriction is that we are using small data and restricted data. So we have made all our data sets public, including 100,000 topologies, 120,000 topologies for this one. For low and high resolution, we are also creating another data set with more than 1 million topologies. which will be made public. But the goal is that eventually we come up with very powerful generative models which can enhance any optimization approach that is out there. And these are just some results where we see that it can generate for even unseen conditions near optimal topologies. And time difference, we noticed that when the resolution goes from 64 cross 64 to 256 cross 256, the time taken by SIMP goes about 16 times, but the time taken by diffusion model only goes by 4 times. And this is important because once we go 3D and once we go even higher resolution, this will make a huge difference in the amount of time taken. And you can see that there is a huge diversity of solutions. So unlike within one generation, it can generate for the same boundary conditions, multiple topologies, which look very different. So each row is all the topologies it generates for the same boundary conditions. Great. So just quick takeaways, generative AI plus optimization on how do you combine generative models with optimization is something we are very excited about, and we think it's a promising approach. We do need better data sets, models, and metrics, and there's a lot of good work going on in there. I started with why should topology optimization care? And I think just to clarify, deep generative models can help amortize the cost of optimization by learning from experience, and it can effectively augment almost any topology optimization approach by giving a better initialization. They can also connect topology with hard to quantify objectives when you want like a topology which looks like your house, but is also, or objectives which are not very subjective. Why should generative AI care? I think TO presents a very difficult test problem, which even the state-of-the-art generative AI models cannot solve, because precision is very important, and precision is a problem of deep generative models. So this is something this is an active area of research, and the CS community learns a lot by solving topology optimization problem. And also large data sets are easily available for topology optimization, unlike other design problems. With that, I would like to thank you, and I'm happy to take questions.
Thank you very much, Faez. Question will come at the end after we finish all the four presentations. So maybe I'll take this opportunity and say that if you have a question, please put it in the chat, so then we can go later and go one by one and address it. Okay, our final speaker is Qian Yi, working with Professor Chen. Qian, are you available? You ready?
Yeah.
Okay.
Yeah.
So she will talk about variational level set method for topology optimization of origami fold patterns. Please, the floor is yours.
Thank you, Professor Waisman, for the introduction. I'm honored to be here today to share our work regarding the variational level set method in the topology optimization of origami folding patterns. My name is Qian. I'm currently a research scientist at the Palo Alto Research Center, part of SRI International. The research I will be discussing today is part of my doctoral studies at Stony Brook. I would like to acknowledge my co-authors, my advisor, Professor Shikui Chen and Professor Xianfeng Gu, both from Stony Brook University. Origami is initially referred to the art of paper folding. With a given crisp pattern, we can fold a 2D flattened object into a complex 3D structure. Thus, origami structures have been used in engineering, such as solar panels, self-deployable actuators, and the furniture such as the foldable lamp. To better understand the origami structures, researchers have been developed some models. One of the well-accepted methods is rigid origami. The key idea is to assume that the origami consists of rigid patches with flexible joints. Another well-adopted way is to model the origami as a truss structures. These methods are usually based on the assumptions that the folding crease is straight and there's no in-plane deformation on the facet area. Recently, the study of compliant origami that consists of curved folds is emerging. For example, when applying origami structures in robotics and other mechanical devices, curved folds are more desirable than the conventional straight folds. It is because they are able to vary the amount of stiffness when interact with different environment and different objects. However, the conventional rigid origami models do not consider the implant deformation and cannot simulate the curved origami structures. Also, design such compliant origami largely relies on the designer's intuition and experience. Thus, in this work, what we want to do is we aim to offer a solution to systematically model and optimize a compliant origami design in order to fulfill some engineering requirements. Here is an overview about our method. Basically, we use a modified shell model to simulate the origami structure so that the implant stretching, out of bending, and the shear deformation can be well captured. For the topology optimization part, we use a level set approach. Here is a flowchart of our method. We first introduce the initial level set functions to represent the crease pattern, and we interpolate the geometry-related information to the shell model for final element analysis. After evaluating the performance, we will do a sensitivity analysis and construct the velocity field to update the level set function and get a new crease pattern. These procedures will continue will repeat until converged to a solution. Before we move to the detail about our method, I will quickly introduce the conventional level set approach for topology optimization. The level set function phi is defined in Euclidean space as an implicit function on one hair dimension. And the dynamic of this boundary evolution is governed by this Hamilton-Jacobi equation. The method has several benefits, including the clear representation of the boundaries and the accuracy in calculating geometric variations. Specifically, in representing origami structures, this means the level set method naturally gives us clear boundaries between folds and facets. And it is easy to adjust the curvatures and smoothness of the folding lines. This is the key idea of how we're using level set implicit representation of origami to represent the origami structures. As shown in this figure, here we use a boundary of two groups of level set functions. One for the mountain folding lines and the other for the valley folding lines. The rest of the area in the design domain is regarded as the facet area. Then speaking of, about the physics coupling, we use a modified shell model. We assume that the folding lines are weaker materials compared to the facet. The value in detail, the value of Young's modulus and the thickness are set as half compared to the facet area. In addition, we modify the local offset plane on the area near the crease with a sign relevant to the crease type as shown in this equation. For example, for mountain fold, there will be a positive offset. For the valley fold, there will be a negative offset. It is well noticed that we use a smooth function to represent the folding area. Such we can guarantee a smooth transition through the thickness direction. We can see our method can handle not only regular straight folding lines, but also more complicated curved crease patterns. Next, we'll introduce a numeric example to show in detail how we formulate each of the objectives. Here we use an origami gripper design as an example. Imagine as a given design domain like this square. When applying force on these two black regions, we want to obtain an origami mechanism where the two target window W would reach a displacement in the target direction, like in this Z direction. We also want to design some origami structures that have minimum crease numbers. In other words, the optimized structure can transfer force and displacement from the input area to the output by deforming the optimized origami. Then let's formulate the objective functions. The first part is a classic kinematic requirement. It means the window area W would reach a target displacement U0. And the second part, G2, is a characteristic requirements. We will discuss the detail in the next slides. And G3 is a total parameter of the folding lines that controls how smoothness of this origami, crease patterns. So let's look into the physics meaning of this G2. Once again, the objective of this part is to generate a pattern that makes the system works like an origami. Namely, first we want the deformation to occur mainly in the area near the crease. This is done by the upper equations. And also we want the out of plane deformation dominates. This is done by 1 over the bending energy, total bending energy, showing the bottom side of this equation. Here is a design evolution on 2D as well as on 3D. We can see the design converged to 2 curved valley folds. And on the right-hand side shows the optimized history. This is the simulation results as well as the realization of our origami gripper. So next, in order, I will briefly discuss the effects of the initial designs. In order to testify the robustness of our method, we rerun the example with different initial patterns, as shown in the figure. Group A only has 1 kind of folding lines initially, and the group B and C have 2 kinds of folds initially set as the initially setting. The total initial boundary number of group B is the same as group A, and group C contains a largest number of initial folding lines. We can see that all of the 3 groups converge to a similar design. Since we know one of the most challenging part in this TO problem is how we translate the behavior of origami structures into the objective function. So here we would like to discuss more how the characteristic objective G2 works to solve this problem. Essentially, the characteristic object is an energy function in order for reaching a design where the most deformation happens on the folding areas. Here is an example to show the performance of the objective G2. As shown in this equation, when we run this simulation, the object function only contains a G2 set, a G2 part under a linear elastic constraint. So the figure from left to right shows the applied boundary conditions, the initial designs, and the final design. The design domain is the unit square, and we fix the center. So in the x direction, we apply the 2 pre-described displacement delta D. And we want to push the model moving toward to the center. The initial design consists of mountain and valley circular folding lines. With the effects of the objective, we can see that the final design changes from the circles to these diamond-like shapes. We can observe that since the parameter constraints are not applied here, we can see a little zigzag on this final design. The figures below evaluate the performance of the given example. The figure on the left shows a convergence plot of each part of the objective function. The solid line plots the total string energy density on the facet area, and the hidden line shows the 1 over total bending energy in each iteration on each iteration number. The 2 plots decreases in the first 20 iterations and then reach convergence and vibrate within a small range. The figure B shows that the string energy density distribution on the final design. We can observe that the highest number happens near the folding lines. So we can claim that our two sub-objectives fulfilled. To sum up, in this work, we aim to provide a systematic way to model and optimize an origami-like structure to fulfill the pre-described requirements. For instance, transforming force or displacement from one pole to another. The origami is modeled as single structures, thus the in-plane stretching, the out-of-bending, and shear deformation can be well captured. And our whole optimization physics is whole optimization process is physics governed. However, currently the work is based on the assumption of linear elastic and small deformation. So in the future, we will consider the large nonlinear deformation. Also in the future, by considering fabricating origami with some active materials, such as ferromagnetic particles and heat-reactive polymers, the work can be potentially extended to design programmable self-folding structures. So this means under a certain stimulus, it allows an automatically switch from the original status to the target shape. Moreover, with our proposed topology optimization framework on freeform surfaces using the extended level set method, we can optimize conformal origami structures on the surface with some desired properties and kinematic performance. So we want to thank the support by our collaborators and funding programs. So thank you so much for your attention. Any questions are welcome. Thank you.
Thank you very much, Qian Yi, for very interesting presentation. Really interesting. I guess now we have some time for questions. Maybe I will ask Amy, maybe can you read